بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone to this fifth class. Before we start, any questions so far? Yeah.
My question is basically about the properties of commutativity.
Yeah. In the assignment, you mean?
No.
In the assignment or in general? Okay.
So there are properties of maps,
Yes.
but then
Commutativity, you mean? Commutativity. Okay.
and yes, so it's a property of a map, right?
Okay. Continue.
So the question is, because the relationship, whatever operation you have there, which serves as a map,
Okay.
functional relationship, we're trying to find if, say, for example, A operation B is equal to B operation A.
Yeah.
And if we have something similar for the associative nature and the distributive
nature,
is it necessary as an additional condition that the output or the answer to each of those expressions are closed under that particular set?
Yes, for sure. Yes. Yeah. So okay. So the question is in the definition of commutativity in general. So commutativity between so when you say A, B, you're always implicitly saying what the operation in between is. So you're saying what you mean probably with A, B equal to BA, you mean the matrix multiplication between A and B. So it's an operation that would take two matrices, A and B, if that's what you mean. And is it equivalent than doing the same operation but reversing the order of B and A? Okay. So if for this operation, so now the commutativity is a property of the operation itself. So we say that this operation is commutative, right? That if you take two elements from the set, it doesn't matter, the order doesn't matter. This is what non-commutativity in the end means. Okay. So if that's the case, if I take, for example, the matrix product of two elements and then I jump out of the set, then already commutativity doesn't matter here, right? Because we want to, if we're using this, for example, to make a group, or we're talking about the group operation, the first implicit condition on the group operation is that it takes two elements of the group and stays within the group, okay? It doesn't jump into a bigger space, okay? This is something you're going to see, okay, when we talk about the special orthogonal group, and you also have it in the assignment, okay? Any other question, Yusuf?
On when to use the special operations, the plus and the minus, and when to use the scalar operations. Sometimes it's a bit confusing where exactly to use it.
Again, operations by themselves don't mean anything unless you say what the spaces are, right? What do they act on? So when you say scalar operation, what do you mean?
So let's say when we come to the
vector space structure, okay. Yeah, addition, the vector addition, okay. Yes.
Is it called maybe R and the normal plus ND?
Exactly. Yeah, exactly. Yeah.
So when do we use the best vector addition instead of the scalar addition?
The scalar addition is an operation that would take two elements of the field, which in this case what you're talking about is an R, and would give you a number in R, right? So 1 + 1 is equal to 2. So this is a scalar, okay, addition. The vector addition is if I give you a tuple of 1, 2, 3 plus, okay, when this is the vector addition you're talking about, plus 2, 3, 4. So one is, okay, how do you define this tuple this operation between two tuples of number, between quotes vectors of Rn? Okay, you know how to do it. Okay, so again,
vector multiplication.
Vector multiplication as an inner product. We haven't talked about inner products at all. Okay, last time we talked about bilinear form, if you remember. Okay, there was a map that takes two vectors and gives you an element in R. So the bilinear form is a general case for what the inner product is. Okay, to be more precise, an inner product on a vector space is a bilinear form that is symmetric, and it's also positive definite. Okay, if I get it, if I remember correctly. Okay, but again, so you see, it's just an example. It's a special case of bilinear forms. Okay, or in other words, it's a special case of 0-2 tensors on a vector space. Okay, any other questions before we move on? Yeah. 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 That's a good point. Yeah. So, so the question is, at some point we talked about linear maps between a vector space V and a vector space W, and then we said let's talk about a special case or a subset of these linear maps between the same vector space. So, linear maps between V and V, we call them endomorphisms. And then we said, okay, let's look at a more special case of linear maps between the same space. We need them to be invertible, and we call these automorphisms. Or the space was called automorphisms on V, and the linear maps themselves, each linear map was called the linear isomorphism between V and itself. How is this, if we're talking about subsets or subspaces of the vector space, how what's inside is not a vector space, while the outside is a vector space? So as sets, the automorphism is a subset of the endomorphisms, and the endomorphisms as a set is the subset of the linear space between V and W as sets. Now, if you try to equip the supersets with some group operation, and then you look at the endomorphisms, it will have the same group operation. But when you look at the automorphism, it will not get this group operation. If you try to give the, sorry, no, what I said is incorrect. If you try to give the outer set, so the linear maps, okay, maybe let's write it down, be precise. Let's see, nope, there it is. Okay, okay, why is it, okay. Okay. Why are there grids here? Okay, let's see. Yep, there's it. Okay, so the question is on the linear maps between V and W, and we said if we have linear maps between V and itself, we call these the endomorphisms on V. And then we said there's another subset of this space, which is the set of all maps in the endomorphisms on V, such that F is invertible. Okay. So this is a subset of this, and this is a subset of that. Now try to make this into a vector space. It will work. Okay, give it some operation, right? You can make this into a vector space. You can make this into a vector space that's a subspace of that one, but you cannot make this into a vector space. Okay, the idea is simply the addition of two matrices, two invertible matrices, is not invertible, right? So that's the idea. So the addition of two n by m matrices is here. The addition, wait a second. Yeah, okay, 1 second. We said that let's assume that V is Rn, okay, just to recap. So if V is Rn, we called these guys, they are Rn, and W, let W be Rm. So these are n times m, these are n times n, and these are the general linear group over R, okay? This is the set of all n times m matrices, okay? This is the set of all n times n matrices. So you can add square matrices, you get a square matrix. But if you try to make this into a group, it will not work, okay? Because when we take, this is a group, but this one, we cannot make it into a vector space, because if the F is invertible, then the n by n matrix representation of this map will have a determinant, okay, that's not equal to 0. And you cannot sum this, okay, sum these and get sub that are GLN and R. So that's the idea. So as subsets, they are within one another, but whenever we equip these with different like structure, it doesn't work. So that's what I mentioned by this is has a vector space structure. This has a vector space structure. This does not has a vector space structure. But I can make this into a group, but I cannot make this into a group. I cannot make this into a group, and so on. Okay. Yeah. Yeah, that's a very good question. Yeah, this is in general. Yeah. So here, this is just an example on Rn and Rm. So again, so finite dimensional, what you think of tuples, but this is in general for all vector space, as long as they're finite dimensional. No, this special set, it has a group structure, okay, when you use the composition of maps, but it does not have a vector space structure. So this very special one. Okay. They can be only vector space. This one can be made into a group, but this one cannot be made into a group. Okay, and it's very simple from here. So I cannot take two n by m matrices and multiply them together, right? So you see, I cannot make them with matrix multiplication into a group. So that's like that's an idea. That's a very easy way to check. Okay. Other questions? These are very helpful. So it's very important to clarify these points before moving on. Okay. No more questions? Sorry again? It cannot be a group over the with the operation which corresponds to the matrix multiplication. That would take two of these and give you another one of these. It does not work. For addition, it can be. And you'll find that if one of the conditions of being a vector space is that this one with the vector addition is already an abelian group. So it's like we cannot talk about vector spaces unless the set with one of the operations is already a group. So it's like a trivial group. It's not really, again, the group in the sense of being with matrix multiplication. Okay.
With scalar quantity only or with
here, okay, this operation, what I mean here, that this is a group, then it comes with the operation that would take two G's and give you one G. Okay, just like when you multiply two n by n matrices, you get another n by n matrix. Okay, if you multiply two matrices that have determinant not equal to 0, you get a matrix that has a determinant not equal to 0. Okay, so you can multiply invertible matrices and get another invertible matrix. That's why this is like it's a group by itself, right? I can multiply again two invertible matrices and get another one. Okay, so that's already the recap of today. So no more recap. So do not save. Now we're going to be talking about manifolds and Lie groups. The aim of this, if we complete all of the material, is that this will be the last lecture on topic number 1 on the math part. Okay, so congratulations for coming this far already, for surviving it. Today, inshallah, will be the one that will it's the last remaining bits that we need to move on to talk about geometric mechanics and geometric control. The last structure we need to talk about is differentiable structure. Okay, we talked about Rn. Okay, different views of Rn. The first one is Rn as a set, which is simply just the Cartesian product of R with R with R with R n times. And we talked about Rn as a vector space, which is a vector space over the field of real numbers with vector addition and scalar multiplication. And this is the Rn you're all familiar with and you use all the time. But you still, when you want to do calculus analysis or to describe dynamical systems on Rn, we need more structure. It's not enough just to think of Rn as a vector space or a set if you want to do more stuff. When we talk about dynamical systems, this is like the fundamentals of x dot is equal to ax plus bu and y is equal to cx. Okay, who does not understand what I just said? X dot is equal to ax plus bu and y is equal to cx. Is that not familiar for anyone? Don't be shy, raise your hand. No one? Okay, so you all know what I mean, right? By x dot is equal to ax plus bu. So the dynamical systems, right? Linear multivariable systems, okay? Dynamical systems that have a linear structure. So whenever you want to talk about dots and you want to talk about partial differentiations, to do calculus, to do analysis, then you need more structure. This structure that we need on Rn is called a differentiable structure. And in general, a set M with this differentiable structure is called the differentiable manifold, okay? Today, I'm going to be introducing manifolds in a very sloppy, intuitive way, not formally, because if you want really to do it formally, we need at least, I would say, like 7 to 8 hours to do it, okay? So I'm going to save that time. There are a lot of references if you're interested to do that, but this is the intuitive definition of what a manifold is. let's start with something you should know, okay? Maybe you don't know it as formally as this, but you definitely, if you passed some math courses, since you're all graduate students, I'm pretty sure you've seen this one way or another. So let's talk about differentiability classes of functions. This is something in mathematical analysis. When you say a function is smooth, or a function is differentiable, or a function is continuous, what do we mean by that? So if you consider a function f that maps some interval of r into r, okay? So this interval, this I, is an open interval, okay? So it can be an open set between two numbers, a and b. It can be from negative infinity to a, from b to infinity, and so on, okay? So it's just an open set. It's an open interval from r to r. Then we say that f is of class C0 if f is a continuous function on this interval. And we say that's class 1 if its derivative exists, if this function, okay, f, its derivative exists, and both f and f prime, with f prime is the derivative of the function, are continuous. And we say that this function is of class ck if its first derivative and its second derivative up to its kth derivative, they all exist and they are all continuous. And if you say you have a function that's smooth, or in other words, it's of class C infinity, okay, just as the name implies, this means that you can differentiate it infinitely and all of these derivatives exist. You're all familiar with these concepts? One way or another, you've seen them before. The same concept can be extended to Rn when we say we have functions of some open subset of Rn to R, then we have a function of x, okay? And x here, we're talking about x as a tuple of numbers, Rn. Then how we say that this function is of class Ck if all of the partial derivatives, they exist and they are continuous and so on and so forth, okay? So you know how to calculate the first partial derivative, the second partial derivative, which is like the Hessian or something like that, and so on, okay? Now let's confuse you a little bit. You all know what a continuous function is if you see it, right? So this one is continuous. It's a continuous function. It says C0 function on R, right? And the other one is not continuous. You all agree? Everyone agrees? What does continuity mean?
At the origin, the derivative is changing rapidly.
Okay.
The first one has a king.
It's not continuous.
It is continuous.
The limits. Okay. Start talking about limits. Okay. If I give you just a vector space structure, as I said, can you talk about limits? You see, that's the first thing. Okay. You cannot talk about limits just with a vector space structure. Okay. You cannot talk about differentiability with this vector space structure. You cannot talk even about continuity with a vector space structure or with just a set. What you need to do that is M should have a set M should have extra structure, and this structure is called a topology. Who here heard about topology before? Okay, who here understands topology? I would say no one. Okay, that's for sure. Okay, it's a very hard topic. Okay, and to really understand what a manifold is and to formally build it up, you need, I would say, 3-4 lectures of each of 2 hours on topology alone, and then you can talk about differential manifolds in another couple of lectures. We don't have that much time, and that's why just take it as it is what I'm saying here. So you can make a set into a topological space, into a where the topology is a set. Okay, so this extra structure that we're giving the set is another set that we call the topology. And if we have a topological space, we can then talk about continuity of functions. And if you can talk about continuity of functions from the definition we just said here, then we can talk about differentiability. So you see here, the C0 is the most basic level, which is continuity of functions on R. You can make this into continuity of functions on Rn. Then you can talk about continuity of functions. Then if you look at C1, you can look at continuity of functions and their derivatives and so on until C infinity, okay? So the most basic level is C0, and C0 you can do it with what's known as a topology. Now, if you have this set plus the topology, which is the extra structure we're talking about without explanation, and it satisfies some properties. I'm mentioning them here so that if you see them in some paper or in some textbook on differential geometry, you know, okay, don't try to understand it, or at least spend some time in it in details. If you have these two, if this pair, which is the set and the topology, they satisfy some properties, which means that they are paracompact and Hausdorff, whatever that means, then we'd call this a topological manifold. Okay, so this is the first time a manifold appears. Okay, so this is the most basic level of a manifold. Whenever you use Rn, okay, so you assume that you have this topology and you use it for sure, and this is known as the standard topology. Okay, and has something to do with circles and with balls of as in subsets of Rn and so on. The question that we're posing here, and we're going to be answering in a non-intuitive, or sorry, in a non-formal way, which is, if we're talking about non-Euclidean spaces, how can we do analysis? Okay, so this is what we're interested in. We're not interested in doing it Rn. Rn you're all familiar with. You do it without thinking. So that what I'm trying to say here is that whatever the math that you're all familiar with as doing calculus on Rn is built on a lot of stuff that are formal, that should be formally like introduced, which is in using topology. You don't think about it, you just do math. How can we extend this doing math, which is taking derivatives and talking about continuity of functions and smoothness of functions? How can we extend this to non-Euclidean spaces? And I'm going to intuitively describe this by talking about atlases and charts on Earth. Okay. So this is an intuitive introduction that will build up the notions that we're going to be needing to talk about manifolds in general. The surface of the Earth is an example of a two-dimensional non-Euclidean space. Okay, and when we say it's non-Euclidean space, means that all over. Okay, if you take the whole Earth as on the surface, we're not talking about what's inside of Earth. We're just talking about the surface of Earth as a sphere, as the surface of a ball. Then S2, which is what just the name for the set of the two sphere, it locally looks like R2, but globally it doesn't. Okay, and this is the definition of S2. We introduced it before, right? You can think of it as 3. Okay, it's a subset of R3. Okay, so the surface of the Earth is a subset of the space it lives in, R3, but it has a condition that any point on this surface or any point on this manifold, it should satisfy this constraint, right? That should be on the surface of a sphere. What does locally S2 mean? Locally, it means that you're at some point, you're sitting here on the surface of Earth and you see it as a flat plane, right? It's locally equivalent to R2, but if you keep moving on a straight line, you don't fall off the cliff unless you're a flat earther guy, okay? But if you keep on moving forward, you start moving with the curvature of the Earth and you come back from the other side because it's a manifold. It has a manifold structure. If you open an atlas of Earth, what you're going to find is inside is just a bunch of charts. Okay, each chart maps a local region of Earth. There is no such thing as one chart for all of Earth. Okay, there's no such thing as one map for all of Earth. Okay, the map you're familiar with that has the Americas on the left and the Asia on the right and so on. This has a lot of wrong stuff inside of it because you cannot take the surface of the Earth and put it on one sheet of paper. And this one sheet of paper is R2 that we're talking about. So, but you can like split Earth into a bunch of local regions, and you can take each of these local regions, put them inside of a chart, and look at it in R2. Sounds familiar? Okay. Consider two charts, one over Egypt and one over Saudi Arabia. I'm originally from Egypt, so I'm biased, and we're here in Saudi Arabia, so stick with it, okay? So we have two charts, one over Egypt and one over Saudi Arabia. A definition of a chart, okay, in the language that we introduced is that a chart is the pair of two things. One is a subset of R2, okay, which is the region we're talking about. We take a subset of S2, sorry, not of R2, of S2. We take a subset of the manifold we're talking about, and we take a map. The map here goes from this subset into R2. The two together, we call them a chart. Okay, you cannot talk about chart only without saying what is its corresponding region on the sphere that we're representing in this bit. Okay, so here what you see in the figure here is that there's a red chart that would map some region with Egypt inside of it. And there's another map called Phi S that would map some region of Earth with Saudi Arabia inside. What is an atlas then? The atlas is simply a collection of all of these charts, right? You should have a very large number of charts, okay? What is the first condition of all of these charts so that you can have a complete atlas? What is the condition? Not about continuity first. Small enough to? Not necessarily. Not necessarily, okay? That's not necessarily. Because here, if we're saying about this, for example, that this part I represented here, stuff that are in between will R2 will work in it, but stuff in here, okay, on the edge, R2 will not be okay very precise. In other words, if you draw a straight line from here to here, okay, and then measure the distance, it will not be the same as the distance really on the map. But if you take a small line here, the distance would be correctly the same on the map, on the actual manifold. Okay, so we're not talking about this distortion of the map. We're not talking about that. The first thing that for all of this chart to make up an atlas is that when you take the collection or take the union of all of these subsets, they should make up the sphere. So in other words, you should not leave any region unmapped, uncharted. Okay, all of the regions on the sphere should be charted to R2. Okay, and then the collection of all of these, we call them an atlas. So you see the collection, sorry, A, which is here represents an atlas, is defined as the set of all charts, okay, where each one of these is a chart, and they are indexed by I because we have like chart 1, chart 2, chart 3, up to some number, and this I lives in some set, okay, so we have, I don't know, 10 charts, 20 charts, 100 charts, 1,000 charts, whatever, okay. Not yet. Okay. Wait. Okay. In the charts themselves, you can have some overlap regions, okay? Because we cannot, again, we want to take some subset of the surface of Earth and another subset of the surface of the Earth, but we're always going to have some overlap regions, right? So in these overlap regions, if I look, for example, on Saudi Arabia that appears here, and if I look at Egypt that appears also in the other chart, so there's an overlap area between the region which I chose to cover Egypt and the region that I chose to cover Saudi Arabia. So in this overlap region, what you see here in purple, the maps, they should be compatible. So this compatibility means that if I measure anything here in this chart, if I measure, for example, the width of the Red Sea from this side, from this chart, and I measure something related to the Red Sea from the other side, they should be compatible. I should get the same information. Okay. So this is roughly what a chart or what the conditions we want to have on an atlas for that it would fit the purpose of describing a manifold or a non-Euclidean space using a bunch of charts and Rn. Is that clear for everyone? Question? Yeah.
For that, yeah, according to because of the distortion, if we take an edge here, it might not be the same distance as here.
That's right, but the compatibility here is that you should be able to go from one to the other. They should be relatable, or in other words, they should be, if they are maps, they should be at least continuous. Okay, so the map that would go from here to here, you need to be able to go back and forth to relate the information here to the relation there. Okay, what I'm saying is that what I mentioned earlier is that if you look at an information here, it's not enough just to look at Euclidean geometry here, because there might be this distortion. Okay, this is captured in something called the metric, which is something we're not going to be talking about, or something called the Riemannian metric. Okay, in general.
Okay. So, Professor, is it that if I'm on a point on the left, I should be able to tell exactly where that point is on the right? Is that what is meant by compatibility?
Compatibility means that if I measure the distance between these 2 points here, okay, and I know how distance is encoded in this chart, it should be compatible with the distance here, encoded here, with the information encoded there, exactly, in that chart. Okay? So that's what the compatibility means. Overlap regions, yes, exactly. Yeah, exactly. Yeah, you can definitely have all of these overlap regions. Other questions? Okay. Now let's take this basic notions, which are you're familiar, it's intuitive from what you know, and put them in some mathematical theory to talk about manifolds. The manifold or a differentiable manifold is the fundamental object in differential geometry. Okay, just like what Rn is the fundamental object in vector spaces. When we talk about vector space theory, Rn is fundamental. When we talk about differential geometry, a manifold is the most fundamental object. An n-dimensional manifold is intuitively a set that locally looks like an open subset of Euclidean space. Just like the surface of the Earth, locally it looks like R2. That's why we say that this is a two-dimensional manifold. Then in general, an n-dimensional manifold locally looks like Rn. But it's not everywhere Rn. Just like the surface of Earth is not everywhere R2. It's not a flat plate. It's just locally looks like R2 everywhere. So this is the intuitive idea of what Rn is. Examples of that of one-dimensional manifolds is the circle. So the circle, if you're living on a circle, if you have something that's living on the circle, okay, imagine that there's a particle here that never exits the circle, then this particle lives in S1. So we call this S1. And we can define it in the same way that we defined S2 and Sn. We defined it, I think, in the first lecture or in the second one. We defined Sn in general to be a subset of Rn plus 1 such that you have that x and y directions or in general are related to each other. The sphere S2 is another example of a two-dimensional manifold. The torus is a dimension, is an example of another example of a two-dimensional manifold. Space-time itself is a manifold. It's a four-dimensional manifold. So locally, when you're studying space-time, you can think of it as R4. You can think of it as X, Y, and Z, 3 dimensions plus time is moving by its own, but in general, not. So in general, space-time works in this region compared differently from a region that's near a black hole, I don't know, somewhere in another galaxy. Space, it's not just about space, also time works differently here and there. Usually you can think of manifolds as being a subset of some Rn, or you can think of manifolds as they are intrinsically. So space-time, for example, is an example of where people in general relativity or in quantum, in general relativity, talking about space-time, they don't think of space-time as living in some Rn. Otherwise, what is this? If we're talking about the universe, what is the universe living in? It's very, again, it's might tinker with your mind. But again, thinking of the manifold itself, space-time is some intrinsic manifold, that works. The same also for the torus. You can think of it as some two-dimensional surface, and there is some R3 that you imagine this being placed in. So imagine that this is a donut on some plate in R3, Or you can think of it as an intrinsically that there are some stuff that live on this surface intrinsically, just like with the surface of the Earth and so on. The configuration spaces of mechanical systems that we're going to be dealing with starting from next lecture, inshallah, they all have a manifold structure like that. They even have some of them have more structure than just a manifold, which is what we're going to be talking about today, inshallah. So formally, what is a differentiable manifold? Or in other words, what is a CK differentiable manifold? Just like what we started with, you cannot talk about differentiability of a function in general. You need to specify up to what order you're talking about. Are you talking about a one differentiability, so a C1 differentiable function, or a CK, or a C infinity? So K here can be 0, can be 1, can be up to infinity. So a CK differentiable manifold is the triple. 3 things: a set, a topology, and an atlas. So the set, you know what the set is. The topology, you don't know what that is. But again, it's the same intuition. It's the same intuitive structure that you give to Rn to talk about continuity of functions on this manifold, without talking about more details. And just as a side note, when we say that M and this set, which is this funny looking O, is a topological manifold, this is the formal way of saying that the manifold locally looks like Rn. So you see, intuitively, you know what it means. What does it to be a topological manifold? But again, if you really want to formally do it, I can point you to some references if you want to do it on your own, inshallah. While A is a CK atlas. We haven't introduced what a CK atlas is. A CK atlas for a manifold M is a collection of charts that cover the entire manifold while satisfying certain overlap conditions. Given this CK differentiable structure, so now this atlas A, along with the charts that are inside, they have some sort of overlap conditions and some sort of differentiability imposed on them in the overlap regions. We call this a CK differentiable structure. And then if you give this structure to a manifold M, you can talk about curves on the manifold, you can talk about functions of the manifold, you can talk about maps between manifolds and differentiability and so on. Okay? So whenever we want to talk about these stuff, which is in other words, describing dynamical systems on a manifold, if the configuration space has a manifold structure, not just some Rn, we need to have this differentiable structure. Okay? I'm always saying you equip it. It's not something that's like a choice that you take a manifold and you try to look for, okay, what structure to give it. Usually there's already someone that already did it. So it either has a manifold structure or not, okay? If it has a manifold structure, you're gonna find whatever maps that come with it and so on. Okay? Let's formally define for a general manifold what a chart and what an atlas is mathematically. The same intuition is what you saw, okay, with the surface of the Earth. This is the formal definitions. Let M and O be a set equipped with a topology. In other words, a topological manifold or a topological space. A chart for M is the pair U and phi, where U is an open subset of M, and phi is a map that would take a region, would take a subset of the manifold M, would go to Rn. But not just any map. We require that when we go to the subset of Rn, it is an open subset of Rn. You see all of the places open. Okay? The reason why we're using open all over the places, this is related to the topology. Okay, so topology is related to studying, okay, maps or studying open sets in general. Okay, so this is why you cannot omit the word open here. You need to put it because of we're talking about the topology which is underlying the manifold. A CK atlas for M is the collection of all of these charts with the properties that M, when you take the union of all of these subsets, okay, you recover the manifold, which in other words, all of the charts cover, okay, all regions on the manifold. And whenever we have in some region there is an overlap, what this says is that whenever you have some region A and some region UA and some region B, that you take the intersection and it's not the empty set. Okay, all of this is just to say that region UA and region UB, okay, they have an overlap region. Okay, there's a place that they overlap in. So in this overlap region, we must have that the transition map, or another word for it is the overlap map, is of class CK. And this map, you can think of it as the following. Okay, it's much better to look at it with a commutative diagram, which I'm gonna plot here. Let's see, annotate here. So now recap that we said that we have a manifold M, and we can have either a subset of it. We can either have a subset UA or another subset UB. Okay. Now from UA, I can have a map that I call phi A, and this will take me to some subset of Rn. Okay. The image of UA under the map phi A is a subset of Rn. And this guy here, phi B, takes me to the image of UB under phi B, which is another subset of Rn. Clear for everyone? Okay, so these two together may make up a chart. These two together, they make up a chart. Now you see that if I have some overlap region, okay, if I have some UA that intersects UB, then I can go with the map in this region, I can go either by the map phi A or the map phi B, right? Because it's in the intersection. So I can go either by phi A or by phi B. And this will take me again to the image of this intersection region. It will be a map of Rn. And this will take me to another subset of Rn and a subset of Rn. This map in between, okay, which is related to the map between the two charts, right? Because this is a chart and this is another chart, or like this is a subset of Rn, which is in the previous example was this map on Egypt and the map, okay, on Saudi Arabia. So this map that goes in between, I can think of it as phi B. It is equal to phi B composed with phi A inverse, okay? You remember we introduced this composition, I think it was the first or in the second lecture, talking about the composition of maps, and this commutative diagram, okay, so this diagram should commute in the end. So if I take some point here and I go with this map, it's the same as going first here and then there. You all agree? So this map here, for this to be a chart or for this to be a CK atlas, I require this map to be of class CK. So if this map is only continuous, then we call this a C0 atlas. If this map is infinitely differentiable, we call this a C infinity atlas. C infinity atlases are, another word for them are smooth atlases. And if you equip a set with a smooth atlas and you have the topology, we call this a smooth manifold. Okay. So, and usually this is the basic assumption that people that work in robotics, or again, with at least in the classical everyday object that we're doing, the first assumption we say, assume M is a smooth manifold, and that's it. So you're going to find that, okay, this is just the assumption. All of this is underlying what all of that means. Okay. There was a question. Robotics, you mean? Robotics? Oh, okay, what's the question? No, configuration space. The configuration space of most mechanical systems, okay, most mechanical systems I can think of have a manifold structure. Okay, so they're locally not Rn. You're going to see it. We're going to be talking about it in the start of the next lecture, inshallah. No, not the workspace. We're talking about the workspace and the task space. Usually they are in Rn, but the configuration space, or in other words, the joint space, will have a manifold structure. Okay, just as a look ahead for what will be covered. Okay, any questions on this part? Clear? Okay. I'm gonna move on with the slides. So if you want to take a picture or take your notes. Yeah. Okay. Do not say. Okay, no problem. Okay. Now let's talk about maps on a manifold. Okay. And this is the part where we're going to be going to the board. Let's see, a whiteboard. Okay. So now let's introduce some concepts what we're going to be needing a lot in the coming lectures, inshallah. So a manifold from now on, we're going to be thinking of it abstractly like this. Okay. It's not a flat space. It has some sort of curvature, whatever that means. We haven't talked about curvature formally. But again, this is a manifold. Yeah, question. That's a very good point. If you have that a manifold is like is closed, again, we didn't talk about what closeness means. We say that this is a compact manifold. Yes. So in general, yes, you can have compact manifolds. If you think of M as a subset of some Rn, you always think of it as some sort of closed, like the torus and the sphere and so on. So these are compact manifolds, so they are closed. But in general, I just draw this to be abstractly, again, but don't think about this as some sort of boundary and what happens when you go to the boundary and so on. Okay. When you think of some curves on the manifold, what does a curve on a manifold mean? Okay. A curve, a point of the manifold here. So a P here is just an element of, we say that this is a point on the manifold. the curve, which is on a bunch of points connected to each other, okay, a curve on a manifold is a map, okay, we're going to be calling this curve, okay, by gamma. It's a map that would go from some subset of R, okay, just again, like what we discussed, some sort of interval, but this interval can actually be closed. So you can have it, for example, it can be from 0 to 1, it can be from A to B, whatever, okay? It can be some sort of interval. This interval is a subset of R, and you go to M. Okay? So if I take a point P, so gamma would map a point P, sorry, it would map some sort of parameter of this interval. Let's call it T. Okay? It will map T to some sort of P. Okay, so this what you see there, okay, is what's mathematically written here. So this point, for example, might be T equal to 0. Okay, and this point here might be T equal to 1. Okay, so if I take gamma of T, so all of this thing is called the curve, gamma, and gamma of T equal to 0 is the first point on the curve. You can think of it this way. And gamma of T equal to 1, or gamma of 1, is the last point on this curve. And again, you can, of course, have loops and so on and so forth. No, the manifold, we give it everything now. Now, okay. If you want to talk about the smoothness of this curve and the continuity of this curve, this is where you need all of the topology and everything we gave it to it, okay? So this is where you need this structure. So that's the first thing. This question? Sorry? P is a point on M. So points on the manifold, we just call them P. Again, P, Q, whatever, okay? So this is what a curve on a manifold means. Easy? Okay. Let's look at functions of the manifold. Okay. So a function of the manifold, F, so this is number 2. So F is a map that would go from M to R. Okay. Which means that it would take any point P, and F of P would be a real number. So these are functions on the manifold. The set of all functions on the manifold usually has some sort of like standard notation. And the standard notation, again, F here is a function on the manifold. And this function can be continuous. So in other words, can be of class C0. It can be C1, can be Ck up to C infinity. Usually when we say this is a smooth function, this means what? It's a C infinity, right? It's of class C infinity. But what does an infinitely differentiable function on a manifold mean? Right? We don't know. But again, we talked about charts. So I don't know how to talk about functions here, but I know how I can take, for example, okay, maybe let's draw a commutative diagram at page. So if I have M here, and I have this function that would take me to R, I know how to take not all of M with a chart. I need to choose some subset of it. Okay, I know how to take some subset of M and then use a chart to go to some subset of Rn. And now you see that if I want to understand what does F mean to be continuous, or what does F mean to be differentiable or smooth and so on, I can simply look at the function that would take me from Rn to R. Okay. So this function is equal to F after phi inverse. Okay. So if you know how to talk about or to study functions that go from Rn to R, okay, and I give you some sort of manifold and you cover all of the regions with charts, again with the atlas that it has, then we can talk about functions, differentiability of functions here by talking about the differentiability of this function from Rn to R. Okay, so you see, this is the drill that will always, you're going to see it again and again and again. Okay? So because this locally looks like Rn, and we have charts that can map us from regions here to Rn, I can do everything that I know how to do with Rn and R and so on with the standard calculus that you know by using this construction. Question. Rn. The M here is an n-dimensional manifold. Okay. An example of a function on Rn, for example, this is just an example. So let's assume f is a map from R3 to R. And I'm going to make up this function as it will take some x, some y, and some z in R3. So x, y, and z are three numbers. And it would map them to x squared plus y squared plus z squared in Rn. That's it. So this is an example of a function. So you see it's a function from R3 to R. Now, if you have some three-dimensional manifold that has another function on it, so you would use the charts to go to R3 and then talk about differentiability of this and so on. So is this function differentiable or not? Is this function continuous or not? You know how to do it, okay? You would calculate the gradient and the Jacobian and blah, blah, blah. We're going to be looking at some examples later on in their context, okay? Question? Functions are maps, yeah. Functions on the manifolds are simply maps from the manifold to R, yes. Okay. The set of all functions. So if let f, yeah.
So for us to know if this function is, the nature of the function is for us to know the nature of f composed with phi inverse.
Yes. If you want to study properties of this function, okay, you can study it in some chart, okay. But it's very important that you make sure that whatever properties you get out of here are independent of the charts that you chose. This is something you see in the definitions a lot. This is in formal definitions in differential geometry. You need to make sure that the definitions you get are independent of the charts that you chose. Okay, so this is an important thing. Okay, question.
So f after phi inverse.
Yes.
It won't be given in terms of f at all. It's a different map expression that's just maps from Rn to R.
That's right.
Not in terms of f.
It includes f. It's f inside of it. Yeah, exactly. Yeah.
But then we can't differentiate. I mean, the property, the differentiable property of f is included in it. But then when we look at it, when we look at the map for the
yeah, okay, I see what you mean. Yeah. The differentiability of f comes from the differentiability of this map. So if you want to say that f is differentiable, prove that this is differentiable in all charts. So this is how it works. Okay. We're going to have an example, inshallah, when we're talking about this. And something that you've used implicitly all of that in is polar coordinates. You all know polar coordinates? Polar coordinates is a chart for Rn that's different from Cartesian coordinates. That's another chart for Rn. More on that later, inshallah. No. Here we're talking about functions from M to R, and the chart maps M to a subset of Rn.
All this within the same manifold.
No, this is only where the manifold is here. So, but this function takes you to R, which is another manifold by itself. Okay, and subset of Rn is where the chart takes you. So you already have this composition or this commutative diagram between three spaces. We're no longer on the manifold itself. Okay. Question? Okay. So let f be a smooth function on M. In other words, f is a map from M to R, and f is smooth. Okay, what does smoothness of a function on a manifold mean? Okay, you know what that means. Then the set of all smooth functions on M is denoted by C infinity of M. Okay, so this is a notation that means all smooth functions on M. So if I want to say where f lives in this place. F lives in this space. Okay, so this is just a notation that you're going to find, okay, in some textbooks, in other papers. Okay. Any question? Okay. Let's look now at maps between manifolds. So if I have a manifold M and another manifold N, and I have a map between them F, if F is smooth and its inverse exists. Now we're not talking about the differentiability. We're talking about the inverse of the map. It exists and is also smooth. We call F is called a diffeomorphism. So if F is smooth and this one is smooth, or in other words, F and F inverse, they both live in C infinity M. So they both, so F inverse exists and it's also smooth. We call F a diffeomorphism. Who saw here this term before? Diffeomorphism? Okay. So this is what the diffeomorphism means. So two manifolds that are diffeomorphic, we usually represent them. We say that M is diffeomorphic to N as manifolds. Okay. You've seen this symbol several times, right? We've seen it between sets. When we have a set, okay, and we say that they are isomorphic to each other, this means that there exists a bijective map between them. If I have two groups that are isomorphic to each other as groups, we say that these two groups are isomorphic and there exists, what was it called between them? A group isomorphism between them. If we have two vector spaces that are isomorphic to each other, then there should exist between them a linear isomorphism, which is a linear map that's also bijective. And here the same construction. If you have two manifolds and you have a map between them that is smooth and its inverse is also smooth. So you see, you cannot just have a map and its inverse. We cannot just have bijectivity here. We have extra structure on a manifold, and we need to make sure that this extra structure is preserved under this map. So this is where the smoothness comes into place. So if this is smooth, if going from M to N is smooth and going backwards from N to M is also smooth, we say that the two sets, or sorry, the two manifolds are isomorphic, or in other words, diffeomorphic to each other. Okay. Question? Infinitely differentiable. Yes, that's right. Smooth means infinitely differentiable. It means it's of class C infinity. Yes. And usually we are going to assume that everything is smooth. Everything is nice, everything is smooth, so that we, again, just to be able to calculate stuff and to do, okay. Let's understand first how the smoothness works, and let's make it our life harder later on, okay? Other question? No. Okay. Because it's gonna take some time. Okay, let's use that time for more, again, let's bulk up all of the concepts, and later on when we come to the examples, again, we're gonna have all of the time at home with the assignments, inshallah. Okay. So now we talked about curves. Okay, so curve is a map from R to the manifold. Maps on the manifold are a map from the manifold to R. We talked about maps between two manifolds. Now let's talk about the tangent space, because the vector, the manifold has something very important called the tangent space. Again, formally defining what a tangent space is requires, again, maybe one whole lecture to do that. Okay, we're gonna do it the intuitive way, and you can do it at your own, in your own free time if you want to know more. So a curve, it's not what a curve should do. Let's undo. Okay. So this is a curve, okay, from that would map T to P. Okay, so it's a curve on the manifold M. This curve now, you see it's changing with time. Okay, so this time here, or this parameter, I can start to think of or talk about differentiability with respect to this time parameter, right? So if a particle is here, okay, if at time t I'm here, then I'm at time, sorry, if at time t equal to 0, I'm at this point, then I'm at time t at this point, and I'm time t plus 1 at that point, and so on, okay? So you see there's some sort of changing with respect to parameter. So it's natural to think of what happens when we differentiate with respect to this parameter. The differentiation of this with respect to this parameter leads us to the notion of tangent spaces. So the tangent vector to this curve here is a vector How it's formally defined, I'm not gonna say it, but intuitively it's just a vector at that point. Where does it live? Okay, let's look at an example with that. Yes.
So as a TP, we are not giving any structure.
A vector is an element of a vector space, so it has a vector space structure. Yes, we're talking about a vector space structure here. I'm gonna give an example with S1. We said that S1 is, okay, is a manifold, is a one-dimensional manifold. So I can be a particle that live here. Okay, so this is at time t equal to 0, and then I can move in the circle. You all agree? At this point, if I'm moving within time, then what is my direction at that point? Upward, right? So this is v at time equal to 0. If I move after some time and I come here, what is my forward? What is my vector? Pointing downwards. Okay, so this is, if this is time equal to 1, then this is the v at time equal 1. Okay, so you see my motion here on the manifold, okay, it's represented by some curve on the manifold. So this is the curve that would take t and give you the corresponding p on the manifold. And the tangent vector to this curve is simply an element of this vector space. Where is the vector space where v lives? Does v live on the manifold? In that case, it's R1. Okay. The case of R2 is the sphere. Let's look at the sphere, the Earth we're living on. Okay. If I'm at that point here at the maybe at the North Pole, and then how many directions can I move in? No? There are two directions only I can move in. Directions as an independent from each other, right? I can move either like this direction, and I can move either in that direction, right? Both of them, they would span some sort of tangent space at that point. So if this point is called P, and this is the first basis I can move in, like the first direction that's independent from another direction called E2, then both of them together, they span what's known as the tangent space to the manifold M at the point P. Okay. The same figure here also holds, so I can draw here some sort of tangent space at the point P to the manifold M. And this is where the V lives in. Okay. The tangent space here is this line, and the tangent space here is that line. Okay. So what I'm gonna say is always true. The tangent space at every point on a manifold has a vector space structure. The tangent space for the circle here is R. Okay. This vector here, I can be moving with 1 unit of speed, or I can be moving very fast, okay, maybe with 10 units of speed. I can be moving with 100 units of speed, right? There's no limit for how fast I can go around the circle, right? The same here. There's no limit for how fast I can go around the sphere, or unless you're Superman, you can go very fast around the Earth. Okay, the same idea. But the motion on the sphere is always either in this direction or in that direction. And this is related also to the longitude and the latitude. Okay?
It is that you mean that for the circle we have only one basis vector.
You have one basis vector. Yes, exactly.
But basis vector has only one parameter r that we use to define multiple basis vector.
All of them have only one parameter r, because the r here, so the curve takes you from r to the manifold. Okay.
What I mean is that for the sphere here, you would need two values on the basis vector to define the position we are on the initial space.
No, no.
One
That span the tangent vector, the tangent space. Yes.
one tangent space.
Yes.
Yeah, for me to define the vector in the tangent space.
Yes.
I will need R2.
Yes, that's right. Yeah, exactly. So here this is S2, right? We said that S2 is locally like R2. So the tangent space has R2. But the tangent space is R2. It's not locally like R2. So there's a copy of R2 everywhere here on the manifold. The same also here. There's a copy of R everywhere here on the surface. of the circle. Okay, so you see it's like the dimension of the manifold is the same as the dimension of the tangent space at every point. So here, if M is an n-dimensional manifold, then it's the tangent space at every point is an n-dimensional. What's the word? Again, if I have an n-dimensional manifold, then the tangent space at any point P to this manifold is an n-dimensional vector space. Exactly. Tangent space. The tangent space, exactly. So the tangent space is simply the vector space where the velocity lives in. Okay, this is intuitively what it is. Formally, again, we need to be there's a lot of stuff that we're hiding here, but this is just the bottom line of it. Question. In the two sphere, you mean? In the circle, S1, okay? That's a very good point. Okay. Let's maybe go to this slide. So the question is the following. So S1, we said that it's a one-dimensional manifold. At every point here, you either live on the so you either have one like coordinate, whatever coordinate mean here, but you have one coordinate that would define where you are on the circle, or you can give it two numbers, right? X and Y. And you're thinking of the vertical velocity and this other velocity that's orthogonal to it, right? This velocity is always what? Is always what? Is always zero. If you think in terms of that this is a subset of R2, so okay, so what you're thinking of is the following picture. You're thinking of this picture now. E1, E2, and this is R2. And you're thinking of the manifold, which is now the blue part, is a subset of R2. That's correct. And you're thinking that every point here, X and Y, have some tangential velocity and some, okay, what the normal velocity. The normal velocity here is always zero if you're thinking about it this way, which defines actually the manifold. You see, the fact that we're only living on the circle is precisely the definition that S1 is a subset of R2. It's precisely the definition. Okay, and something you're going to be seeing in the assignment or in the homework, that the definition of the tangent space, okay, at every point is related to the fact that the normal velocity component in R2 is always zero. Okay? Yeah.
Going back to the two sphere.
Okay.
So when we're defining a tangent space, we can only define a tangent space at a specific point.
Yes.
So now, based on the vectors that live in that tangent space, obviously, the tangent space is a vector space. Now, the collection of all the tangent space,
yes,
is also a vector space.
No, the collection, okay, the collection of all tangent spaces, if you take them together, okay, and create what's known as the disjoint union of them. We talked about disjoint union in the first lecture. Okay, I'm gonna be formally introducing it next lecture, inshallah. The collection of all tangent space, or in other words, the disjoint union of all of these tangent spaces, they make up something called the tangent bundle. Okay, so the word tangent bundle in differential geometry is simply the collection of all tangent spaces. You put them together in some sort of bag, okay, in some sort of set. You call this the tangent bundle. What is the structure that this bundle has? It's another manifold. Again, if you remember what we discussed about that when you have, for example, linear spaces between vector spaces is another vector space, this is the same. So when you take all of the tangent spaces, put them together, they have a structure of another manifold. That manifold has twice the dimension of M, okay, just for your information. So this is what a tangent bundle means. If you have tangent spaces, you can talk about what? What was something that was always associated with a tangent space? No? No? The other than the basis, we introduced something called the dual space, right? So at every point, because we have a tangent space, we can also have to this tangent space a cotangent space. The cotangent space is simply the dual of that vector space, whatever that means. But all of this will appear later. The last thing I want to say before ending up is, if M has an extra structure of a group, so if M is a manifold and at the same time it's a group, we call this anyone knows? Nope. A Lie group. So the term Lie group that you see all over the place in robotics is simply a manifold and the group at the same time. Okay, and these Lie groups are very, very special. Okay, and this is the topic of next time, inshallah. We're going to be not talking about Lie groups in general. We're going to be talking about the corresponding Lie groups that are very important for robotics. These are SO3, okay, or SON in general, and SEN in general. The special orthogonal group, which is a Lie group, and the special Euclidean group, which is another Lie group. Okay, but that's it for today. Okay, let's end the lecture, and if you have any questions, I can take them offline. Okay, let me just end because if people want to run. Okay, thank you very much. Assalamu alaikum.